Then we've got some discussion and questions.
I just want to, if you want to do this practically, practical implementation, there are a couple of things you can do with assembly levels. If you go down the variational approach, you have to be doing minimization, and to minimize this cost function, we need to know the cost function and its gradient. There is a result we are not going to derive today, but we'll discuss it later. But this gradient of the function can be found by running one forward, and it's a tangent linearized version of the model followed by a joint. So one forward and backward integration that gives you the gradient. And in principle, when you start here, the gradient is given by this expression here. We had the cost function. We differentiate the cost function, we get this here. And if we put this to 0, is equal to 0, that is the condition for the minimum. That would be your analysis. And then if you move things around, then you would get some condition for xp in terms of h of x and your observation difference in y minus h of xp. And that would be your analysis equation. And the coefficient which we get out of here would just be what is, it's called also Kalman gain. You think about it as a weight function, so which weights your forecast information and your observation information.
So in order to derive this, you said you didn't want to derive this?
This is no, the adjoint that we get the gradient from forward and adjoint calculation. To derive that, I would have to go through. Well, the only way I know how to do that is to go down the route and derive the Euler-Lagrange equation for the system. That's a whole other lecture itself. So you can probably also find some control theoretical approach of deriving this. But for the moment, the interesting thing is that we need the gradient, and for this is the expression for gradient. In the gradient, we have replaced. Remember now, we have a nonlinear problem. We want to solve a nonlinear problem as a sequence of linearized problems. All these operators here, like H transpose, even the model, are now acting on perturbations, delta x, from your guess. This would be a linear model acting on perturbations in this time frame. And these H here, that is just the Jacobian, that is the first derivative of the operator with respect to the state, or if you make a Taylor expansion, it's just the first terms in Taylor expansion. So therefore, h of x becomes this h, this Jacobian, applied on delta x. So now it is not a function of it, it is a matrix acting on the perturbation. And the transpose of that, which takes you from observation back to model, that is the terminology here for that is actually tangent linear and adjoint codes. And when you're working at algebra, it turns out that adjoint of an operator is just its transpose. Let's see how we get this. There's a good introduction there at the bottom. The whole thing, how you derive this for the Lorentz system, is shown. There is also a link in your presentation. So we're trying to understand in detail by doing yourself for the Lorentz system. It's quite useful to follow what they've done here for the variational analysis. The way we work usually is, I mean, you can only get so far by working with the continuous operators because they don't really represent what is going on in your code. The only thing which represents that is your actual code line by line, which is actually the numerical representation of your model equations, or in this case, the numerical representation of your observation operator. So a very fruitful way of thinking about your code is to think about each line of your code as an operator. And for example, if you have if h of x is an interpolation operator, then if you have a few lines in your interpolation, then each of these with the subsequent line, the total observation operator is just this sequence of very simple operators. So the way we derive this, we have a nonlinear expression. It's usually very simple for each line of nonlinear code to derive similar linear version. And the adjoint of that, which is just transpose of this, it's also very simple. That is just the transpose of each of these individual operators here, each line, apply the reverse, of course. And that is also quite simple to derive. Once you know the thing that you just go through that in reverse and derive the adjoint. This can be difficult if you have some non-differentiable functions, like some within our convection, parameterization, or condensation terms in metrology. It can be tricky, it can be done, but one has to be very careful. It can be tedious because if you have long models, this can be quite a hard work. But actually, once you do it in pieces, one subroutine at a time, it's quite okay. And there are some automatic tools, I gave some links to that, which can use to do the hard work for you, even doing things linear, even the adjoint. But of course, like with all these automatic tools, you have to look at the output because that may not give you the optimal in terms of computational speed. So it's just, but it can be a good first step in the process. So the main result we are going to use is that the gradient of the cost function, the gradient of the cost function, can be evaluated by using, you make one integration of the forecast model, and when you make the integration of the forecast model, each time step, you calculate this observation minus h of x. That gives you observation term. And the adjoint model then integrates all these contributions from the observations back to the initial state, where they're compared with the background state at the beginning. So the point is that if you do minimization, you need between 10 and 100 iterations for the thing to converge. And if you take into account that the linear model may be twice as expensive or 1.5 points as expensive, and a joint model 3 times as expensive as a nonlinear model, you end up with, let's say, 4 times, just to do one minimization, let's say over 12 hours, you end with 4 times 12-hour forecast equivalent. You need to do this 100 times, you end up with equivalent of between 20 and 200 days of model integration. It's not very useful if you just got 1 hour, like you got later prediction, 1 hour to get everything ready and then do a forecast. So the way we solve that is that we use something which we call the incremental algorithm. It means that if this is a nonlinear state here, this may have very high horizontal resolution. The linear evolution, let's say, needed to do 1 forward and 1 adjoint integration to the minimization, in each of these linear models into a much coarser resolution. And then when you do it that way, given that you go to 2 or 3 dimensions and you can increase the time step in proportion to this, it turns out that by doing this approach, doing this minimization in a much lower dimension, you can actually get everything read in very quickly. So that is a very important concept, that you, when you do the minimization, the minimization doesn't have to be at the same resolution as your full model. You still compare observations with your full model at the appropriate time, doing the first forward integration, as you do, to get the guess state for each linear model state, which you're going to minimize. But you can basically cut the cost by a factor 10 to 100 by reducing the dimension of your problem. And then, but you iterate that several times, so you will get to a proper solution. And the way it works is a little bit like this. So this is your main model, which you now integrate at full resolution. So let's say that you collected observations in this interval. And then what do we need? We need this comparison between observation and model. That called y minus h of xi. You calculate that for a nonlinear model. You interpolate the nonlinear model down to the lower resolution. And then you linearize your linear model around this interpolated state here and do this minimization here, iterative minimization algorithm, where you then are working on these perturbations delta x until you come to some minimization criteria, interpolate that delta x back to the full state, and you can repeat this again. So this is some kind of a multi-level time-saving algorithm, this incremental approach. And without this, you couldn't really do anything in metrology. It's very essential.
But how did you calculate the HT? Is that involved at all in this approach?
That is HT you get from discomposing the matrix.
Yeah. But then you have to have these individual little HTs.
That is one line of the code. You know that.
But this is just one vector. You need a matrix. So you need different realizations or something at least.
No. You think about. Okay, they are applied sequentially, but you think about your observation. You think about the whole subroutine or whatever, which is doing your observation.
I mean, I'm thinking of the right-hand side or something. But you want a matrix, not a vector.
Yes.
So how do you get this?
Yeah, because in 2 dimensions, in 1 dimension here, h, x, h of x, this is the h of x on the x2, it is for 2 model variables. Okay? That is alpha x1 plus 1 minus alpha x2, yeah? That's
It's a y. Now we're calculating y.
no, you use h of x. So
Yeah.
this is like
Yes. For example, yes.
so yes.
If it's a linear observable, yeah.
So and the way to think about this is I see what you mean. Equal to. Let me just first on the, just as abstracted from that it is h or whatever. You have a statement like x1 is a x1 plus b x2, yeah? So what you're really solving is that x1, x2 is equal to a, b, x1, x2, 0, 0. Okay?
X1, X2.
No, one, sorry. This is equivalent, yeah? X2 doesn't change. X2 is x2.
Yes.
X1 is 8 times x1 plus b times x2.
Yes, right.
Okay? Now the transpose of this, you should just, x1, x2, if you call that the adjoint variables, that is equal to a b 1, 0, x1, x2. So that's a little bit how we work. If this is a tangential statement, this becomes your statement. So that so that means actually that x1 is x2 is did you get this right? X2 plus b times x1, yeah? That's
Yeah.
so that's
Line is with stars, right?
yes. It should. I'm putting stars and everything here. Stars and everything. It's an adjoint variable to separate them from that. So this is how we work in practice in the code. You look at one line in your nonlinear code, okay? So one line in the nonlinear code.
1 times that, you mean?
Yeah. One times that. For example, so like this. x1 equals a times x1, x2 plus b times x1.
Yes.
Something like that, okay?
Yes.
This is your nonlinear model. Then we derive this tangent-linear expression. So the tangent-linear expression is, now we remember we went to this framework that we have actually replaced x by xp plus delta x, yeah? We linearized around xp, okay? Let's put that in there. Then we have x1. Okay, let me just put that index up there just for now, so we don't mix the 1 and 2 below that. X1 is x1 b plus x1 equals 8 times x1 b plus delta x1 times x2 b plus delta x2. Too much right, let's just keep this up. So it is enough to illustrate. And if you expand this, you just get a x1 b x2b, which is equal to that, plus a x1 b x2 plus a x b x1 x2b. Following so far? Okay, so this is how we work then. So then we've got the tangent linear here, plus some higher order terms, of course. Higher order terms, which are going to neglect. No. So then, in the tangent linear model now, this goes out against that, so we have got the expression here that written matrix from x1, x2 equals this thing here. We could A dx1 dx2, that's what we want to solve here. Okay, dx1 dx2 is equal to, first we have 2 by 2 matrix here, A times A times x2 background this one, the x2 here, this is what we want to get. So A times x2 background dx1 plus A x1 background dx2, yeah? And this is so, yeah? Okay. So this is what I do. I went to there, I derived a linear code for this one line of the code, and then the adjoint code comes from itself, but just substituting the adjoint variables here, doing a transpose. So just the x1, the x2 transpose equals ax2 b ax1 b01 the x1 the x2 transpose. So what I do, I start with the nonlinear code. Each line of the nonlinear code, I do this thing linear. If I see some efficiency, I group things together. Sometimes it's best not to do that because other people, even you see it yourself, when many people working on the code, can become confusing if you do things too efficient. So, well, it will be optimized later on. But during development, it's sometimes best not to do things until at the last moment. And then my tangent linear routine will look something like this here. This is tangent linear routine. And then to get the adjoint, it is like row 1, 2, 3 to n. To get the adjoint, we actually work in reverse. I do this process, transposing this matrix, starting from row n minus 1 to row n. That is just because the transpose of A times B is B transpose A transpose. So this is really all there is to tangent linear and adjoint code development. The only trick which comes into this is sometimes you have things which are more complicated than that. And sometimes you've got some very tricky processes which may be sort of switches, almost like on-off processes. And we know how to linearize that, but you need to, sometimes you need to keep things in memory, what branch you took when you made this switch. So that makes things a little bit complicated. Actually, a better approach, what we try to follow is, actually this is like model improvement. If our models include a lot of these switch, very nonlinear processes, we try to rewrite this particular part of the model in turn to give equivalent results, but these are more linear. That's quite often, a lot of development involved, but that's quite often successful. And it's quite often the best way of doing things because you really, well, you get much better description than of your tangent linear and adjoint.
So by AD you just mean the successive multiplication of these little HTs?
Yes.
And by TL you mean the successive multiplication of the ordinary H?
Yeah, maybe successive application. It's more applied operator on each other.
It's matrix multiplications.
Yes, exactly. Matrix multiplication. And the trick here is that I At each step, even if, let's say, only one variable is involved on left hand side and several variables on the right hand side, you need to write the left hand side in terms of all the variables, because then you can do the transpose, as we saw here. But you have to think about this expression as x1 is 8x1 x2, and x2 is equal to x2. And then you can transpose this stuff. Well, of course you can. So
it's more costly to write the code, the adjoint code. You have more operations.
You have
Even
more
some are fake or not fake, but they are kind
Some-
of artificial.
yeah, some are artificial, and some are quite like in this very simple interpolation. In the forward direction, interpolation, you combine 2 points into one. In that joint, you need two separate statements, taking a contribution to one point and to the other point. So there's duplication there directly. So that is why.
But there is something you didn't mention, that there is some zeroing of some of the variables at a certain point in the adjoint code. And that was something that confused us a lot when we were writing ours. When do you zero things? When you don't?
Yes.
Because
It-
you use the same names for all the variables, right? In writing the code. The direct variables
Yeah.
are called the same in the adjoint computation, and then you need
Yeah.
to be careful.
No, but
to
we don't mix, in the same configuration, we don't mix the two together. We may use the same name, but because in the finite linear, I mean, you've got one name for this nonlinear state which you're linearizing about. That you can treat as more of a constant. That is some time evolution constant. We are linearizing perturbation on top of that. In the forward direction, I mean, and you do that, and then you do the adjoint. You don't mix the two together in one integration. It is more like, how do I explain it? Yeah, I think it comes more, let's see, explain that. Let's see. Why do we zero things? There's an illustration in this. I think we have an example from there. This is this example of the Lorentz model is quite used to look through. And they actually have included the code and some examples, plottings and different things. The whole process, everything is in there, including some sensitivity experiments and things. So we play with that. Code it on the computer and play with it on the airplane. So, let's see. Yeah. Let's just take a very simple statement. So you've got x1 and x2 that are variables. Somebody in the code make a statement x1 equals x2. Okay? Can happen. You see? Now, what this is actually x1, x2 equals 0, 1, 0. Yeah? Yes? What's the adjoint of this? Adjoint of this is just x1, x2 star equals 0, 0, 1, 1, x1, x2 star. So in the adjoint, we come to the conclusion that we have to, that x2 is x2 plus x1, and you put x1 to 0. And so this is, I don't know why this exactly comes, but this is somehow a function of that. You are using, you're making successive steps in an algorithm, and all the variables of course get sequentially updated for each line. So therefore it is very careful to have a compatibility between the forward and the adjoint equation. You have to keep this very much in mind, so that really where it is implied that the variable should be 0, it must be 0, if it is used somewhere else in the code. If it's not used at all, you can skip it. But formally, you should always put it to 0. If you have some kind of equality statement, it should always be put to 0, the variable which you, in the adjoint code, this x1 variable, it should be equal to the forward one. Otherwise, the adjoint will be wrong. Okay, so this is
About, can I ask about the previous? So what's the forecast here? How to make the forecast from this?
okay.
Because you saw the data for just estimate initial state.
Yeah. Now the way we do this,
That makes sense.
let's take this box here and call this just A for analysis. So there the way we work in practice, of course, to get these things going is that we put the timeline here. And these are our periods over which we collect observations. Okay? Now, for each of these, make our first analysis using observation this, we get some initial state, we make a forecast.
How long?
As long as we need to. We make for 10 days. For example, we are collecting observations over 24 hours or 12 hours. Then we make a 10-day forecast, for example.
Yeah, but to start, from, that, initial point, why don't you start from the last point? Because it also
It's the same thing. In the strong constraint model, it's the same thing, because this is you're minimizing everything in this window together. So it doesn't matter where you start from, because it will be the same evolution in the end.
Okay, so how will you estimate the probability of your forecast?
Let me come to that just in a moment. So what we do here, we do this, and then of course, this here will then be the background for our state here. Make a new estimate, make a forecast, and this will be a new background here, new estimate, and forecast. So on it goes. And then how do you estimate the probability of this? We do it by comparing with observations in later windows. And basically by doing with observations at a very short range. So you can, in this period here, you can take this forecast here, compare that with observations. Then you get something which is like y minus h of x is your background. You can make statistics of that. And then you see, at least in terms of observation, how you can compare if you have improved things or not. If this is larger than in some previous experiment.
A posteriori, right? The probability.
Yes.
If you make, say, tomorrow 10% of chance of rain.
We cannot make a statement about whether there will be 10% probability of rain from a single forecast. What we have to do then, and what we also do in practice, is we run several forecasts with slightly perturbed initial conditions. And from there you can say something about the probability.
So you do some Monte Carlo simulations.
Yes, that's what we do. So at each instance, we do actually, today, we do, let's say, a high resolution forecast, but we also simultaneously initialize a cloud of forecast, which then ends up something like that. and then from there you can make some estimate of the probability of rain above certain threshold.
So it's only you have to repeat all the whole speech, right? From
Yes.
Bavaria and
Yes. You can have some outputs.
then you will also do some variations, you know, at each divisional point, right? So that since you collecting data, so every time you collect data, you have to.
You mean for this ensemble?
Yeah, for example, yeah.
You can do it in two ways. One way is to do just this high resolution analysis, and then you randomly perturb the initial condition, and you add a stochastic component to your model, representing your model error, and you run your, say, 50 forecast forward independent of time, and you repeat, and that will give you then your spread, your PDF. You repeat that at each analysis time. Another approach is you run, let's say, 10 or 50 different analyses at a lower resolution. Remember the incremental approach. We can always do things at lower resolution. We can afford that because the problems becomes so much cheaper when you reduce the dimension of the problem. Let's say we make 10 or 50 independent analyses. In each analysis, we do as you say, Sasha, and perturb the observations. Use and do the different analysis, slightly different analysis, 10 different analyses, or 50 different analyses, and then run forecast again from that, still using this calibration stochastic part in the forecast integration. So that's another way of generating this initial condition. Okay, so this is very much a field of development. How do you realistically get some initial spread, this represent your PDF, your uncertainty?
Right, yeah, but also for forecasting, you can need also to estimate uncertainties. You need some future, right? Simulate some future durations. Do you use this or not? Because you can, you have, you know, that high resolution, right?
Yes.
Integration.
Yes.
But then you can kind of use this to simulate future durations and estimate uncertainties.
Yes, you can
You
do
do
that.
this?
Yes, we use that
Uh-huh.
approach also. But of course, you only can do this after the fact. So a few days later.
Or future, simulate future durations by adding errors or
No, you can.
to future.
Today, I mean, if we do this, it is after the fact. So of course, we have things like reanalysis, where we actually analyze things going back to 1940 or 1900, using all observations available. But if I understand correctly, we have a given framework, which is today. We collect observations for the last 12 hours. That's what we do. Then make a forecast. Then the result of this forecast, you can compare with tomorrow's observations tomorrow. Or am I misunderstanding?
We discussed about how understand prediction. It is you try simulate possible observations for future.
No, you have to forecast, and then how to make uncertainty of this forecast in a situation. Yes. If you predict
That
a size
is-
number, we need to put some, you know, error bars in prediction,
Yes.
right?
Yes. The only way we know how to put this error bars is statistically. And we can do that by, we make statistics of comparing this forecast from here. We compare the observations in all ranges up to day 10, or whatever a forecast range is. We calculate the correlation between observations and RMS error between observations and forecast. And that then gives us a curve which usually looks like this, that in time, for a given parameter, of a given height, you can get, for example, something like the RMS, for example, of the wind, at some height, let's say about 5 kilometer height in the atmosphere, that may grow something like that. That's what you get, RMS. Now, if you want to go further and say, on the particular day today, what is the predictability in 5 days' time? That is an unsolved problem. how do you predict your predictability?
Well, the predictor say, that tomorrow the infield, let's say, 10 meters per second plus minus
Yes.
5, plus minus means 1 sigma deviation.
Yes.
But
That is what this kind of gives you.
I mean, it should correspond somehow to the spread of the cloud, the predictability.
Yes. Yes.
So why is that not a solved problem?
No, it's not so problem because, first of all, the cloud, to get the spread of the cloud correct is a big problem. And, in particular, on average state, you're right. Things work. The only time you're interested in these things is on a non-average state. When things suddenly develop differently than they were yesterday. And what happens to...
Therefore, I understand that the predictability is time dependent. But numerically you have a recipe for finding it out.
Well, that recipe only works in a trivial situation because normally we start out here. It's our initial cloud, and we do our forecast and end up something like that. Two problems. First of all, what guarantees that the size of this here is same as what it should be? This could have collapse, and that is really what very often happens with these kind of ensemble approaches. That this, instead of being the real thing, maybe looks something like this. So it doesn't really take into account the full variability, but because of different assumptions, because you have not spanned all the directions of your initial conditions, you only have got maybe 50 members, and you've got maybe 5 million dimensions to play with. So you can only make a Monte Carlo simulation of a few leading dimensional instability, and then you may get it wrong. The second thing which may confound you is that it all works very well, except that it looks like this, except that on this particular day the evolution was actually like that. And this is typically what happens in where you have very low predictability, and you cannot predict this by the size of the spread.
The reason for it going wrong was not because because the correct trajectory was not within your initial test sample. It must have been something else.
Well, it has to do with it's just a non-linearity of the system. If you think of the lower system, very simple thing. You have these two attractors, and you're sailing around the one attractor. You get very close to minimum. You are in other attractor. Very small differences in end up in the old one. What we would hope, if we have a good system, is that we would have let's say, some probability of this and some probability of that as well. That is the ideal situation. That our PDF represents these things. But and when we see situations like that, then we say, oh, it's very unpredictable. And sometimes it works, sometimes it doesn't. And we don't really have a handle on when this picture is reliable, when it isn't.
But isn't the difference just that in this new picture you would be saying there's a 40% chance that the weather becomes bad and a 60% good chance that the weather becomes good? In the previous case there was a 0.1% chance that the weather becomes bad, and that's exactly what happened in that particular case.
Yes. I mean, so ideally, but I just want to separate between what the ideal is, which is this, compared with reality, which is more like that.
But if you can increase your ensemble size to very large, then probably you will get the right thing, but that's not practical.
Yes and no. It's very difficult to pick out from your ensemble what exact perturbations, even with many dimensions, what exact perturbations you would like to give it to get to span all the possible future evolutions. It will be better to have larger than smaller, but in practice it actually saturates at some level. Increasing it after that doesn't help you much. That level is quite low actually. Seems to be somewhere order 100 or something. You don't need to go much beyond that. Even a complicated or simple system. Yeah, so all I want to say here is that yes, this is the idea that we can do this, but please be aware of that our experience is a reality. Well, it's very difficult to capture the real few events which you're interested in where things really go wrong. It's just nature of the system somehow.
But still probably want to make a forecast after this Monte Carlo simulation.
Yes.
You don't use precise solution, but use some mean value or no?
Yes.
Use a mean value after because the distribution maybe.
Yeah, when we make the Monte Carlo forecast, we are not really that interested in each individual value, because that may be all over the place.
Right.
And we are more interested in the distribution of the values. Are they all located here, or are they, as you suggest, are they in two different clouds? And that gives us that information. So you can look at the mean or the median of these values that we give you. The median and the spread.
Decide which to take, right? So that
yes, and ideally you would then say, is your forecast 50% probability with this, 30% probability with that, 10% probability with something else? That's how you do that. But I just say that it's very intense development in that field, and I don't think people have found the final answer yet. But
current approach pure numerical, so just do Monte Carlo.
sorry?
The current approach is just pure numerical, right? So just simulate numerically.
Yes. 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 Yes, but what else can you do really?
One Kalman filter.
Yeah, but that is the same thing.
Huh?
Kalman filter is the Monte Carlo approach also. Well, ensemble Kalman.
Yeah, but Kalman filter provides also estimates, right?
But it will apply only if your equations will be
Estimates.
Well, yes. From the something we haven't gone through here. In this evolution one time to another, you can also include the evolution equation for your errors, which will only, well, in the Kalman filter framework there are two limitations. Kalman filter assumes that you just got random noise, and you will a linear evolution of those noises. In practice, that may not be what you want. In practice, you find that the most interesting errors are those which have some structure to them, maybe systematic errors, and that's what we need to do. And what we do then is in the extended four-level framework to include model errors also, include model errors with structure. So that's so it is true that the Kalman error can get the Kalman error framework can derive this kind of errors. And the way we think about it now in metrology and oceanography is you take a hybrid of the two, where you think about it that as if you have a Kalman filter, but each step of the Kalman filter you do a 40 bar. Even you can think about ensemble Kalman filter. You have ensemble of different analysis. Then you use the spread of these different focus of these analyses to give an estimate of your sigma, your focus error variance. It's too much to ask about the focus error correlations because too big dimension. You estimate the correlation statistically. Use these variances in your single high resolution analysis. So, and then you mix the two together. So it's like, so you can have an ensemble Kalman filter of 40 bars. Because in ensemble Kalman filter, it consists really of two steps. It's just analysis equation. It's the same thing here. Expression which you get when you have a cost function, put the derivative to 0, you get that expression. That is your analysis equation. And then following is a sequential update, which is forecast and the forecast error evolution to the next step.
But when you do this, in the ensemble Kalman filter, you are applying to a smaller dimensional dynamical system. So the error matrix you get is actually smaller dimensional than your bigger full system.
In ensemble Kalman filter, what we typically do is we take, first of all, we take a limited number of ensembles, order 10, 100, not more than that. Then your errors you don't try to evolve the full errors. You maybe do some kind of singularity composition of the full space and try to evolve the leading eigenvectors of your evolution, maybe 100 leading eigenvectors, describe those. So you see that you get a limited expression for the errors. Then the rest, like in 40 bar, you need to estimate statistically. So we go like this. Okay. Can you show summary? Summary. So, what I want to show you, what I've shown is that this maximum likelihood approach is a very nice approach to think about combining models observations. And through the concept of the observation operator, you have flexibility to consistently basically put in any observation you can think of. As long as you can think of a link between what you observe and any combination of your variables. And this three-dimensional variation of data assimilation, four-dimensional variation of data assimilation, this is just two variables of the same thing, derived from this maximum likelihood approach that is minimizing a cost function. And the only difference between both are iterative methods. The only difference is that in 3D VAR you assume all observations, compare observation and model at the same time. In 4D VAR you compare observations with the model at their appropriate time. And actually there are hybrids between those two, so you can actually have somebody halfway house between 3D VAR and 4D VAR. And you could, in principle, solve this all. If the dimension is small enough, you could just write down the linear equations, solve it directly. As I say, there's a submatrix or something, but we prefer to solve it globally with iterative algorithm, which has been in practice found to be the best way, the fastest way of doing things. And another way to get things fast is to solve your problem as a look at the nonlinear problem as a series of linear subproblems. Then you use the output from the one linear problem as input to the next, and you solve this linear problem at much reduced resolution to the original problem. In our case, for example, the horizontal resolution is can be 10 times smaller. Usually it's about 3 times smaller than the full resolution. So 3 by 3 by 3, that's 10, that's about 30 times cheaper. That's right. Well, I don't level 2. Anyhow, it's order of magnitude cheaper. And what I haven't gone through here, of course, we need a precondition. That's what I tried to say, that we need to divide by the variance of each variable, otherwise you get the equal-condition problem, it won't converge. Another factor is p. And we have assumed the model will be perfect, but you can also do the same exercise with imperfect models. But I would say, while one is learning these systems and training on them, there's no point in doing that, because usually the other 2 points are the most important ones. You get the observations in, and you know the estimate of the initial condition. These tend to be the dominant error parts. You want to get those right. And then you can add on model errors later on. Okay, so there's more here. Well, which is something that I didn't go through. Something which you mentioned about biases. They're actually, you're saying here that this kind of approach is used by all major focus centers. And the main reason for that is that, to be honest, the main work in this data simulation isn't so much developing the algorithm itself. It's more incorporating all different types of observations in this algorithm and incorporating right control decisions, quality control decisions for these observations, and estimating the systematic errors. So these three components, quality control and estimating systematic errors of observations, is really where, and develop observation operators, is really where a lot of the development is. So over 90% of the time taking data simulation, I would say. And that is why they use this variational framework, because it's a very general framework to, you can reuse the same framework for any type of observations. So it's in the initial, first it is a bit of a labor-intensive thing to get the thing up and running. And once you got it up and running, it's a labor-saving device, because you get the very systematic way of introducing any new observations. So anyhow, so this is what they haven't covered. What is quite important is to, in your case, I think, how do you calculate these B matrices, especially when you have models with a quite, you have limited observation information. So that is quite important how you can do that. And also from observations, it's quite important how you can include biases, systematic errors in observations. Very important topic, but I mean, hopefully one can have some static assumption on that to start with. And I mean, this is not a topic which I would put on top of my list if I were developing things to start with. I mean, but it's very easy to include in the training.
Well, in our case also we don't know parameters of our system, estimation, parameter estimation. There's also a problem there.
Yes.
Can be equally or more important than determining the state of the system. Because we don't know what coefficients are and all that.
I mean, I was just discussing this with Axel. We were discussing this here. There are basically two approaches to this. One is optimistic approach, I would say, which is that we write down, let's say, expression for the uncertainty in our parameters and try to, let's say, find the optimum parameters. That may work in very simple systems, but I think you will find that in the real systems, there's a very, very involved, through the nonlinear dynamical system, very involved relation, indirect relation from the parameter value to what you observe. So it may be very difficult to invert that relationship from observations back to the parameter. But so what we tend to do is more, let's say, kind of a verification approach, where you try different ranges of the parameter and look at the output and verify that against the observations which you have.
But you can do some preconditioning, right? By doing this.
Exactly, you can do some preconditioning.
But then you can put parameters as your state, system state.
You can do that, yes. And we do.
In addition to temperature, you put the diffusion coefficient, right? So,
yeah. I think this works well for parameters where you have a fairly linear models. If you can write you say, I want to estimate this parameter as a function of whatever this thing. Okay. If you have, like, say, some kind of a say some globally some large scale global model for your parameter, then this is quite feasible. This is what we do also. We include this exactly. But some parameters are more difficult than others. Like in our convection parameterization, if you try to adjust critical parameter in a convection, for example, coefficient which determine, for example, in a given column how much air is transported from surrounding columns into this column through subgrid scale convection, is a very sensitive parameter, and your results could be all over the place if you try to include this in the minimization. It's such a non-linear relationship. So in practice what people do is that they maybe do very high resolution simulations of a single column, try to see what's coming in and out of there, get the first idea, go back to full model, try it there, tune it up and down, and compare the observations, see what agrees best, and see what agrees best under all different kinds of conditions, stable to unstable, on the layer, and all over the globe. So that's an iterative approach, which involves very high resolution models and the full model, and maybe even some preconditioning by doing some parameter estimation as you did. So you can use all the tools you want. But I'm just saying that you want to make a point that this, what you suggest, is one of the tools. But then we use all together, and the final arbiter is that the focus you get corresponds better to the observations, or the simulation corresponds better to the observations for a large number of cases.
Small standard procedure, you have to choose a node.
You have to choose, unfortunately, yes, because usually the difficult parameters tend to be things which you can't resolve explicitly anyhow, like for subgrid scale processes, which you have to make some assumptions on how you represent these physical processes in a bulk parameterization. You know, you have maybe some idea of the PDF, and you integrate that upwards until you get some single number. Like if you look outside today, you will see clouds, and we are trying to represent 25 by 25 by 100 meter or 1 kilometer layer by one single number, cloud cover. If you look at the cloud cover, you see it is very, very heterogeneous. But what we are trying to represent is what is the mean effect of this cloud cover, or mean effect of the cloud cover distribution on the mean parameters in surrounding, or the mean parameter over the whole region. So it's a little bit like thinking about, we are really thinking about it's a mean of an ensemble approach somehow.
We had some previous discussions with Oliver. He said that there are two communities. That one is data simulation, we estimate multi-state of the system, and another part is parameter estimation. Some people believe that once you estimate parameters, by placing parameters, which just integrate the system and make a forecast rather than doing this simulation.
Yes, yes. I think that the most work which I've seen on parameter estimation tends to be on smaller systems.
On small systems.
Yes, I mean you do it in a simplified system, and it's maybe something which you can learn from. But I would say that in your real systems, it is a part of the one of your tools. It's not the only tool. It's one of several tools. It's a good tool to use among those.
But it can easily happen that that the models will always be wrong in certain things. I mean, when I'm told, for instance, that precipitation is over continents versus over oceans is always wrong. I mean,
yes.
Because there is maybe some of the physics is not represented in
You're exactly right. What was your name? I mean, I'm not in this community. I'm very sorry.
My name is Fritz Busse.
Okay, thank you. Elias Holm. I don't know what it is. I know what's talking to you. No, you're exactly right, sir. The thing is that this is how we work. We get the feedback, exactly like this you say. We look very carefully at the output of our forecast. We, for example, see that, in stable boundary layers like in winter over Northern Europe, you may get things wrong more often than not. So we need to see what part of our parameterizations are sensitive to this, how can we improve those? And in particular, when I say land-sea differences, how can we see to that the critical parameterizations perform, let's say, equally well in both conditions? Some things will inherently work better over ocean, because you've got very homogeneous, nice, very constant surface in tropics, for example, and over land they've got a very heterogeneous land surface coverage, etc. Sahara across, but
So you want to answer? If we go into the quality of forecasting, for me I have two big problems with the current work. But perhaps for weather, you do compute model with the spherical harmonics up to 800, but that's where you are right now. But for example, for the climate and what they have done at the GIEC, the hydrocore with which they describe the weather and the turbulence is perhaps at Lmax of 80 maximum.
Yes.
And that's a big problem because you have a big effect of turbulence and the way you are resolving your turbulence and your flow that goes into the problem of being able to do forecasting. And we know turbulence is a difficult problem. So the question is then how confident you can be by having all these very complicated models that include feedback from the trees, the water cycle, all the chemistry, and at the same time the turbulence is described like the poor man's. And so you see, I'm wondering at which extent if they were doing a simulation with 800, Lmax of 800, will they get the same answer? I don't think so. I think
no, we won't do that. And this is exactly the point that there is, I mean, you have to get some minimum resolution. We, like, if you say that this L80 which you refer to is basically 160 grid points around the equator, that is a bit low. If you go to about 300 grid points around the equator, that kind of grid, and do climate models, you get a jump in performance. When it comes to the effect of turbulence, of course, we always are working with parameterizations. We cannot describe turbulence explicitly, so we are describing the mean effect of turbulence on the effect of, let's say, our assumed level of turbulence on mean flow. So we have some turbulence model. And of course, the size of the contributions varies with your resolution. And we try to take that into account. Current models which are running globally, we are approaching like something over 2,000 points around the equator. So we are getting down to about 15, 20 kilometers, something like that.
Yeah, but that's for weather forecasting.
That's weather forecasting.
But for climate modeling, then we are in trouble.
For climate modeling, yes.
I think we have very few points. So the question is then when we are taking into account ozone and all these problems, and there is another one that comes from the solar physicist, is the forcing from the UV light.
Yes.
We know that as a function of the solar cycle, the total irradiance is varying by a tenth of a %.
Yes.
But we know that in given wavelength, like UV or more energetic one, like for example X-ray, or the variation can be up to a factor of 50.
Yeah.
And that has not been taken into account. So I'm not even sure for the weather models you are doing multi. When you take the solar forcing, you are not taking the solar forcing as with different wavelengths. You just take a total irradiance, no?
We have a wavelength model from UV to infrared.
For the solar, and you take into, you don't take into account the variability coming from the magnetism.
No, that is usually on time scales which is
too large to. But for climate, that's important.
For climate, yes. But yeah, for climate we have a lot of interesting issues, I would say. And one of the issues for climate is the turbulence. But the exact value of, let's say, few terms in your radiation code can, and for example, interaction between radiation and clouds can change the bias of your, well, change systematically your climate simulation. So climate simulations are a much harder problem to get correctly because you have to keep the model on track for a few hundred years, and you cannot really be confident of that yourself.
I guess they are giving a kind of, they are trying to do ensemble prediction. I think the approach of the climate communities or the GIEC is to do an ensemble. is to say, okay, let's vary the parameters within a certain range and see if we get +2 or +10 degree over the whole globe, even if it doesn't make much sense to speak about an average temperature. It seems that global warming will be more local, and you could have also global cooling at certain places, you know. So it's not a homogeneous distribution over the globe, let's say. But what I'm concerned with is that sometimes when I have this presentation by people who are doing either weather forecasting or climate modeling, it's even more true for climate modeling, that you have put a lot of sophistication in your models in terms of feedbacks from plants and all this carbon dioxide cycle and all these things. But you are lacking basic hydrodynamical processes that could, you know, offset you.
No. We have an approximation of the Navier-Stokes equation. We have an approximation of all turbulent processes, both internal in the atmosphere, due to stability variations and also interaction with the surface, under layer. But of course, like in any numerical code, well, actually, at a given resolution, you're limited by what you can parameterize. But there is turbulent parameterization always present. Otherwise you won't get far.
I guess you have done some DNS run where you are comparing your DNS run to this approximation or primitive equation, as you call
Yes,
them.
and our models usually perform better on DNS run compared to observations.
So the primitive equations are better than
Primitive
the DNS?
equations with turbulent parameterizations tends to be better than
DNS.
And the simple reason for that is that in DNS you have too many parameters to play with, and they're not in tune to the same degree as in focus models. If you would take a DNS model and really compare it with observations and really fine-tune the parameters for a very long time, for several years, you would probably beat that. But it's also that turbulent DNS is a limited area, whereas you have the whole interaction with surrounding areas in a...
Well, you could do a global DNS.
Yes. They've done...
That's what we're doing. I mean, I'm doing that. I know it's possible.
They tried to do that.
But it's difficult.
But the results so far look completely different from...
Okay.
Because because the important thing is not just get... The important thing is never to get one process right. The important is to get a good description of all processes, and the quality of your whole forecast will be determined by your least, by your worst component. So you get perfect parameterization of turbulence. If your cloud parameterization is not good enough, or is weaker, your result will be limited by the performance of the cloud parameterization. That's how it works.
Okay. That's interesting.
Parameterization is empirical, right?
It is mostly empirical, yes. It is based on, it is based on physical understanding of the process going on, based on that you go out and measure things, maybe at very high resolution, make some theoretical modeling of this, and then try to integrate that upwards to the larger scales. And then when you make that integration, then comes the empirical tuning of things to get best agreement with what is observed.
So, to go back to our problem of solar physics, and I will discuss it a bit at lunch with the sunspot.
Yes.
Right now, we know that the equation to evolve the magnetic field that comes from Maxwell's equation is the induction equation. We have this equation.
Yes.
As I told you at lunch, we miss the machinery that goes from the induction equation to sunspot emergence, or to the statistic of sunspot emergence.
Yes.
So what you seem to be advising us to do is to try to do a kind of statistical study or some tuning of this emergence process, or to try to fine-tune, not necessarily to have the physics that will explain sunspots, but to have actually the kind of recipe to have sunspots in our models, to then try to fine-tune these parameters to give the most realistic emergence?
No, it's not quite how we work. It is more like that we would have we are fine-tuning what we cannot resolve. We try to integrate forward in time with our model equations what we can resolve. Like some of you must have some kind of a global solar, at least for a convection layer solar model, yeah?
Yeah.
Okay. And the resolution of that is
About right now we go to spherical harmonic to about 1000.
okay. So then you integrate it forward, but you have probably several unknown processes or unknown source terms in your equation. You may know that there are source terms, but you may not know the magnitude at a given time.
Yeah, because they are dependent of Reynolds number, Prandtl number, this kind of
No,
physical parameters.
I'm just saying that, as I understand it, you have a lower boundary condition. A lot of things may happen there, maybe on short time scales.
You mean the tachocline?
Yeah.
You're meaning this shear layer at the base of the convection zone? You mean?
Yes. Things must happen there.
Well,
Which affect.
Axel doesn't agree necessarily, but let's say that in the broad community we will say that things are occurring in the tachocline.
I mean, you may very much have a situation like we have in the atmosphere, that we have the atmosphere, we have the wave model, and the behavior of the wave model is very much determined by the atmosphere. But when we are trying to simulate things, because the wave, that's in principle dissipated system, the wave model. But when we try to do assimilation observations, it's very useful to do the assimilation separately for both systems and then run it together separately, because that somehow tends to improve the whole consistency. How can I explain this? Yeah, we also got other things. For example, in our low boundary condition, we have the sea surface temperature for, let's say, short focus ranges up to 10 days. We may just assume the sea surface temperature to be constant. That does not necessarily have to be correct. If there is an intense hurricane, that may change the temperature locally, right? A lot that may somehow, it may feed on this temperature change and become even more intense. So I'm just wondering if, like, even if you have some situation like that in solar physics, this makes it difficult that you have maybe no observations of your lower boundary condition, and things which happen, they may be affecting things further up.
But really we have no observations.
Well, we have some clue. I mean, we have seen some oscillation in the tachocline, but do we believe them or not? I'm not sure. But we have through seismic probing, we have some clue of what's going on inside, but more for the flow than for the magnetic field.
You come back to your question. What you asked was, do we want to do some kind of statistical regression between, let's say, sunspot activity and something going on? What we tend to do is more in terms. We try to model what we can explicitly to the resolution we can, and then comes the statistical thing for processes which we cannot know exactly, or which we can only observe the mean effect of. We try to make some parameterization of that. I don't know if it makes sense in your case to look, let's say, of the mean instead of trying to simulate individual sunspot. Is the mean of sunspots over a larger area or something like that? I don't know if that makes sense.
But
That's a little how we would go.
Sasha with Ian Stanflo did a very nice analysis of active regions and how the tilt of this active region as a function of time, because the active region, when they emerge on the sun, they are not oriented east-west, they have a small tilt.
Yeah.
It's called Joyce law. And so they have done a statistical study on how this Joyce law will occur. At the same time, I discussed with Marc De Rosa and Carolus Schreiber in Stanford, and they have done this standard model, which is not a complete model. This is a very simple model based on statistics, where we are making popping up active regions with a given statistic of this Joyce law. We have a kind of observational distribution of sunspots that emerge at the surface. And they make this model run, and it does look quite interesting, the results. So I'm wondering if we're not in a situation now where we could perhaps try to put into 3D models some of this kind of more statistically influenced by observation things to put in the models and see, but we like to do things self-consistently normally in astrophysics. We don't like to put things by hand.
I have a question to Sasha. How you can include statistics for your Taka client? If we
but you could put, for example, you could have a function that put toroidal fields at the base of your convection zone by hand on a very regular time scale that is close to the solar cycle, and see how this can modify. You see?
We have not a relation to observational data. Of course, we can put on Taka climate what we want really, and can obtain very different results.
I don't think the tachocline is a problem by itself. I think the tachocline is a sheer layer.
No, for example, tachocline.
No, I mean...
All we don't, we need just to operators M and H, and then you can just apply it. It's up to you to construct these operators.
I mean, it's true that the question is how do you improve the models, and can we... So, for example, these are the questions we had with Olivier Talagran and Lauren, we were discussing when we were developing our alpha omega variational model. That what will be the interest of such a model for us? For example, could we use sunspots to invert the meridional circulation? So the flow, the equivalent of Hadley cells that we have in the sun. So could we use the emergence of sunspot at the surface to actually know some things about a flow structure deeper down by evaluating the model? Say, okay, this model, you see, use that as an inversion procedure, because you can do these kind of things, you see, and that's where, so you can think about it. So it can go both ways. It can give you constraint on things you don't know, but it can also be used as trying to fine-tune parameters to get more realistic predictions. So I mean, both approaches are interesting. One is perhaps more physical than the other one, I don't know. You know?
I suggest maybe we can make a coffee break, and then I guess the failure society today.
Thank you, anyway.
And then we can, after coffee break, come, you can ask questions.
Yeah. Thank you for your very